Welcome to Empowered Learning. This video is the second video in the series called Finding Derivatives by Using Differentiation Rules. So in this video, what we're going to do is use the differentiation rules that we studied in the part 1 video to actually do some application examples. So here is our first example. We want to find the equation of the tangent line and normal line, that is to say, a line that is perpendicular to the tangent line. So that's why I have this, that is to say perpendicular line, but it's actually perpendicular line to the tangent line. To this curve, y is equal to 1 plus 2x quantity squared at the point 1, 9. Okay. So if we think about this, we need to find the equation of a line. It just so happens that that line is going to be a tangent line. So what we're looking for is something of the form y is equal to slope of tangent line times x plus some y-intercept. Okay. Now, one of the things that you should know if you're watching this particular video is that the slope of the tangent line is going to be equal to the derivative of the function that we're dealing with at a particular x value. And since we're given the point 1, 9, we're going to use the x value from there to figure out the derivative or the instantaneous rate of change or the slope of the tangent line of this function at this instant or at the 0.19 or at the x value x equals 1. All that stuff means the same thing. So first thing that we need to do is find out what is going to be the derivative of this particular function and then evaluate it at 1. So that's essentially what I'm trying to get to. The next thing that we need to know is, well, what is this normal line? We need to find the equation of a normal line. So if we find the equation of the normal line, it's going to be of this form as well. But note here, the normal line has a slope that is going to be, basically the line is going to be perpendicular to it. So the slope is going to be the negative reciprocal of the tangent line. Okay. And so if you remember back in algebra, we know that the relationships in between two lines that are parallel, parallel to each other are the same. Slopes of lines that are perpendicular to each other are the negative reciprocals of each other. So that's what we're saying here. So if we know that the slope of the tangent line is going to be the derivative of our function here at 1, then that means that the slope of the normal line, which is slope of the line that is perpendicular to the tangent line, is going to be negative 1 divided by the derivative of this function evaluated at 1 here. Okay. So we're laying all this out now so that we know what it is that we're looking for. So most important thing here is to find out what the derivative of this function is. Okay. So now that we have all that together here, if you remember from the part 1 video, if I take the derivative of this function, then what I'm essentially doing is taking the derivative of this function, and when we expand this function out, it's going to be 1 plus 4x plus 4x squared. And if we take the derivative of that, for the first term, we get 0. Second term, we just get 4. And third term, we get 8x. So we essentially just get 4 plus 8x. So what this tells me is that the derivative of this function evaluated at 1, meaning if I was to draw what this function looked like, and I was to draw a tangent line through the point 1, 9, then the equation of that tangent line would look like this, and the slope of that line would be what it is I'm about to calculate now. And so the slope of that line would be 12. So what this tells us here is that the equation of our tangent line is just going to be 12x plus some, y-intercept. And we could use the point-slope form of an equation of a line to figure that out, okay? So here, just to kind of compile everything before we get into finding the normal line, we know that we have a point 1,9, and the slope of that line would be 12. So here, to find the equation of that line, we have y minus y1 equals m tan, or slope of tangent line, x minus x1. And of course here, this would be where our x1 and y1 would be. So this is y minus 9. Slope is 12, x minus 1. And of course, if we add 9 to both sides after distributing in both terms here, we would have y is equal to 12x minus 12 plus 9. And that would be y is equal to 12x minus 3. And just want to make sure I did all the math right here. Yep, so that would be 12x, and that's minus 12. And then this would be a plus 9. Yep. So this would be our equation of our tangent line. All right, so the next thing that we need to do is find out what the equation of the normal line would be, okay? And so for the normal line, go ahead and do some separation here. For the normal line, we know that the slope of the normal line is just going to be -1 divided by whatever the slope is I got from the tangent line. And that's just going to be a -1/12. And again, we have the point 1,9. So y minus y1 equals m norm times x minus x1, where again, x1 and y1 are going to be the x and y coordinates of this point. We'll get here that y minus y1, 9 again, -1/12 for the slope, x minus 1. And here this will be y is equal to -1/12x plus 1/12. And then if we add 9 to both sides here, it will be plus 9. And of course, here we just need to add this together. And so that would be the same as 9 and 1/12. I'll go ahead and rewrite that. It's the same as 9 and 1/12. And of course, we know that 9 and 1/12 as a mixed number would be the same as 12 times 9, which is 108, plus 1, which is 109, divided by 12. So we're going to change this mixed number here to just being 109 divided by 12. And so this would be the slope of the, sorry, not slope, but the equation of the normal line. And so this would be our answer for the equation of the normal line. This would be our equation for the tangent line. All right, let's move on to our second example. So for our next example, we're asked to find values of a and b, and we're assuming that a and b are real numbers. We want to know what values of a and b is the line 2x plus y equals b tangent to the parabola y equals a times x squared when x is equal to 2. Okay, so before we actually go and work out this problem algebraically here, we want to try to take some time to understand what this problem is actually asking us. Okay, So we're going to switch screens here just so that we can kind of work out conceptually what this means. And then afterwards, we'll work it out algebraically. All right, so I've kind of rewritten a summary of what our problem is asking us for here. And so the first thing we want to recognize here is that we have a parabola that we're dealing with. And we're trying to find a line that is going to intersect this parabola here at a single point. So the first thing here is that since we have A here, we don't know what A is. There are two possibilities of what this particular parabola could look like, with it being a parabola and a function. So here we could have this case where our A is greater than 0. Or we could have this case here when our A is less than 0. Basically, the parabola opens up when A is positive. Parabola opens down when A is negative. Now, we also know that we have a point that this particular parabola is going to, a point that the tangent line is going to go through on the parabola. Okay, so I'm going to go ahead and draw that here. And it's going to be at x equals 2. So I'm just going to assume that it's on this side here. So okay. Now I'm going to switch this up a little bit later, and you'll see why. But for right now, I'm just making that quick assumption here. Okay. Now, if we look at the information that's given to us here, we know that our line is going to be 2x plus y equals b. Now, using a little common sense here, we think, all right, well, we don't know everything about this line, but we do know the slope of the line, okay? And if I was to rewrite this particular equation here, it would look like this. Y is equal to negative 2x plus b. So one of the things that this tells me is that the slope of the tangent line is going to be negative, okay? So since the slope of the tangent line is negative, then what I'm looking at here, if everything's going to be the same here, this wouldn't be a possibility, meaning that my point couldn't be on this side of the parabola here, because remember, I'm trying to draw a line through here, okay? And the line that I'm drawing right here with my cursor would be a line with a positive slope. It would have to be a situation like this if the parabola is opening down. It would have to kind of go down like that, okay? So I was trying to get it to actually go through that point, but I didn't do a good job of that. So I'm going to try that one more time here. So if I got this, and it's going to kind of go like this through that particular point. Now, notice that if this is going to be true on the other side here, then the point would have to be on this side of the parabola if my line is going to kind of go through it like that, okay? So just conceptually speaking, wherever this line is going to be placed, if my A is positive, it's going to be on the left side of the parabola. If A is negative, it's going to be on the right side of it, okay? So kind of know that. So the next thing here that we want to look at is that we know that in either one of these choices, we don't know which one is going to be because we don't necessarily know what the parabola is going to look like. We see here that the parabola is y is equal to ax squared, okay? So this kind of gives us a clue as to what this is going to look like. Notice that y equals x squared in general looks like this if A is positive, and is going to look like this if A is negative, okay? And so if I'm looking at this strictly at when A is equal to 2, then I'm either looking at one of these two situations here, and if the slope of the tangent line is going to be negative, then it has to be this situation here. So because of that, I know that this is no longer being considered. Okay. So I basically have a parabola that's going to look like this. That's going to have a tangent line go through the point when x is equal to 2, like how you see here. Okay. So that lets us know a few things before we start doing our work algebraically here. So first thing, we know that a has to be negative based upon the mathematical context clues we've been given. Okay. So we know that. Now, the only other thing that we need to find is here, we know that there is a point that this goes through. So we need to figure out the corresponding y value for that so that we'll know the point. And once we know that point, we'll be able to find out the equation of this line, because the equation of this line has a slope, and that slope we already know. It's -2. So we can find the y coordinate for this particular point, use that slope. We have slope, point. We can find equation of line using slope point formula. Okay. All right. So now that we understand from a conceptual point of view what it is that we're actually looking for, and now that we have a strategy, algebraically speaking, to figure that out, we're going to go ahead and work out this problem algebraically now. All right, so we know from what we saw earlier here, this could be rewritten as y is equal to -2x plus b, which in turn lets us know that the slope of our tangent line is going to be equal to -2. Okay. We also know here that we need to find out the corresponding y coordinate here. So here we know that y of 2 is going to be a times 2 squared, which is 4a. We know that. Okay. So here we're still stuck with the situation of figuring out, well, what in the world is a? I know a's got to be negative, but what is it? Okay. Well, let's look at the derivative of our function evaluated at 2. Okay. And so to do that, let's first just look at the derivative of our function on its own. So if I look at the derivative of this function on its own, the derivative of ax squared is just going to be 2ax. And if you remember, the derivative of our function at a particular x value is going to be the slope of the tangent line of that function at that point. So here, if I say derivative of this function at 2, this is going to be the same as the slope of the tangent line here, because remember, we're looking at it at x equals 2. So what this tells me is that here I have 2a times 2, because x is going to be 2 in this case, that has to equal to slope of tangent line, which is -2. And so from there, that would be 4a is equal to a -2, which in turn means that a is a -2 over 4, which is a -1/2. Okay. So here we know that a is equal to a -1/2. So 1/2 of what it is that we need to find out has been found out. Now, notice that because a is 1/2, that also tells you that y of 2 is going to be 4 times that -1/2. Okay, which is just going to be a -2 at the end of the day. So now that we have this, then this tells us that the point 2, -2 is on the graph of y of x. Okay. Now, the only thing that we need now is we need b. And notice here that we have 2x plus y equals b, which we have rewritten this way. Since I have an x and a y coordinate here for a point on the graph, and I already know the slope, all I need now is to use these two coordinates here in this equation, and I can find out what my b is going to be. So therefore, y equals minus 2x plus b. We know that y is going to be negative 2 equals negative 2. X is going to be 2, and then plus b. Of course, all this ends up being a minus 4. And if we add 4 to both sides, we have 4 minus 2 equals b, which means b is equal to 2. So our answer here is that a is equal to 1/2, b is equal to 2. And so what this means now is that we have the line 2x plus y equals 2 is going to be tangent to this parabola, y is equal to negative 1/2 x squared, at the point 2, negative 2. Okay. So another way of rewording what we've actually done is to say that sentence that I've just written, which is the line 2x plus y equals 2 is tangent to the parabola y is equal to negative 1/2 x squared at the point 2, negative 2. All right, let's look at our next example. So this next example that we have here is one, if you are a first year calculus student, you will see this example a lot because it's tied to the maximization or minimization of functions here, okay? And so we don't talk about that at this point, but just letting you know that anytime you're asking anything about horizontal tangent lines of a function, what you're really trying to figure out is where does your function have peaks and dips at? Or where's your function max out at? Where does it minimize at within a certain x value range? So here when we say for what values of x does the graph of this function have horizontal tangent lines, another way to reword that is at what values of x does your function have peaks or dips in its graph? Okay. Now, without knowing too much about this function, since and I'm using pre-cal knowledge here, since I know this is a cubic function and I know that the leading term is a 1, I know that the end behavior of this function is going to be a lot like x cubed. And since I have all these extra terms in here, I can tell you that the graph of this function is going to look something like this. Okay. Not quite sure where these x-intercepts will be, and that's really not my concern right now. But I do know that the graph of this function is going to look like this. Now, the reason why I'm bringing this up here is because do you see that my function, it has a peak right here, and it has a dip here, okay? And notice that if I was to draw a tangent line through both of those points, that would be what's called a horizontal tangent line. So this is why I said that this function, this problem here, when they ask for horizontal tangent lines, what they're really asking for is the places that I have peaks and dips at on my graph. Now, just from pre-cal knowledge, I know that I should come up with 2 answers. So when I do the work for this problem, I should have 2 answers, okay? Now, I'm not necessarily sure if one of them is going to be negative and one of them is going to be positive as far as the x values are concerned, okay? Not really sure about that because I don't know exactly where this function is going to lie. But I do know that I should have 2 of them. And I do know that the y-intercept for this particular function should be at 3 because of this 3 here. All right, so how do we find the horizontal tangent lines? Okay, well, first of all, we need to find the slope of the horizontal tangent line. And of course, the slope of any horizontal line is 0. So we know that the slope of the tangent line for the lines that we're talking about here is going to be 0. But we also know that to find the derivative of the tangent line, we have to take the derivative of this particular function, okay? And the one thing that we don't know is going to be the x values where the derivative or where the slope of the tangent line is going to be 0. So that's what we're actually going to solve for, okay? So what this means here is that we take the derivative of this function. And so using the power rule, the derivative of the first term here is just going to be 3x squared. So we're going to say derivative of this function. First term is 3x squared. Second term is going to be 6x. Third term is going to be 1. And then the fourth term is going to be 0, because derivative of any constant is 0. So from here, we set this equal to 0, and then we solve. Now, this looks like a regular quadratic equation from pre-cal or college algebra. Of course, we have 3 different options on solving this type of equation. We could either try to factor, we could do completing the square, or we can use the quadratic form. Just looking at this, I don't think we're going to be able to factor this real clean. So I'm going to elect to do the quadratic formula here. Okay. So quadratic formula minus b plus or minus square root of b squared minus 4ac. All that over 2a. And this is going to be where a in this case is going to be 3. B is going to be 6. And c is going to be 1. So ax squared plus bx plus c. So all we do now is just plug and chug, and we see what we get. So we have a minus 6 plus or minus 6 squared minus 4 times a times c. All that over 2 times a plus or minus 6, and then this will be 36, 6 squared, 4 times 3 times 1 is just 12, all that over 6, and of course the radicand there is going to be 24. And since I know that 24 is 4 times 6, I can rewrite this as square root of 4. Oops, didn't quite turn out the way I wanted there. So this will be square root of 4 times square root of 6. All that over 6. And we'll come here, and we know square root of 4 is just 2. And at this point, you kind of have a choice on how you want to rewrite this. I'm going to do it both ways. I'll factor out a 2. And of course, 2 goes into 2 once, 2 goes into 6 3 times. So you'll either have this answer, or if you wish, you can go ahead and rewrite this as 2 separate terms. And this will be minus 1 plus or minus square root of 6 over 3. And of course, you could rewrite it in another way as well, but either this way or this way will be acceptable. And so what this looks like here is one of those values is going to be x sub 1 that I have labeled up here, and the other one is going to be x sub 2. So, of course, the -1 minus square root of 6 over 3, that will probably be the negative one that we see here. And the -1 plus square root of 6 over 3, if that ends up being positive, and it should be, then it will be the one that's over here. And so what we found are the x value locations where the graph of this function has a peak or a dip in its graph. All right, let's move on to the next example. So for this next example here, we are asked to find the equation for a second degree polynomial. So basically, how can we characterize that function algebraically? And we're asked to figure out what that specific function is given some certain properties about it. And so in order for us to find this particular polynomial, there are 3 unknowns that we have. Since we have 3 unknowns, we need 3 equations. And as you see here, we have 1, 2, 3 equations. Since we have those 3 equations, we could figure out what these 3 equations are actually telling us. And then from there, we can use those 3 equations with 3 unknowns using systems of linear equations, or in this case, nonlinear equations, to be able to figure out what A, B, and C are. So that's essentially the strategy here for this problem. Now, conceptually speaking, what this is telling us is that here it's telling us that I have a point 2,5 on the graph of this particular polynomial here, second degree polynomial, quadratic function. Okay, so this function here has a point 2,5 on its graph. The second thing that it's telling me is that at the point 2,5 on its graph, the slope of the tangent line is going to be equal to 3 at this particular point. Okay, so translating that another way, if this was a particle moving, it's saying when the particle is at the position 2,5, the rate of change of that particle is increasing by 3 whatever units per whatever. Okay, this third equation here is, and we haven't officially talked about this yet, but it's telling me about the concavity, or put another way, the rate of change of the rate of change. And so this is going to be at 2. So if you want to think about this as position, then here this says that, hey, at the position 2,5, I have a velocity of 3 whatever units and an acceleration of 2 whatever units. Okay, so that's another way that you can think about this. So now that we have that information here, let's actually figure out, well, what does P of 2 equal 5 look like? P prime of 2 equals 3 look like? And P double prime of 2 equals 2 look like? Okay. All right, so I'm going to erase all this business here, so it'll give us a little bit more room to actually do the work. So what we're going to do is figure out what all 3 of these equations actually entail here. So first equation, P of 2 is equal to 5. If we plug that information into here, if I put a 2 here, then P of 2 is 5. And everywhere where I see an X, if I put a 2 there, then I know 2 squared is 4. So that's 4A plus B times 2 is 2B plus C. So this is my first equation that comes out of the information that's given to me. Next thing that we need to do is figure out, well, what is the second derivative, the first derivative and the second derivative of this particular polynomial here. And so to kind of make life simple here, I'm just going to go ahead and do it here. So the first derivative of this polynomial is just going to be 2ax plus derivative of bx is just b. The second derivative is just going to be the derivative of the derivative. And the derivative of constant 2a times x is just going to be that constant 2a plus derivative of constant b is just going to be 0. So it's just going to be 2a. So what that tells us here is that for our second equation, the derivative of this particular polynomial at 2 here equals 3. So what that means here is, if I'm looking here, derivative of function at 2 is 3. And that's going to equal to 2 times a times, here, I got a 2 again, plus b. And so that tells me that 3 is equal to 4a plus b. So that is my second equation. For the third equation, second derivative at 2 is equal to 2. And of course, now we're using this equation here. So if I let x equals 2 here, second derivative at 2 is going to equal 2. So it'll be 2 is equal to 2a. And of course, we know if we divide both sides by 2, this lets me know that a is 1. So now that I have all this information here, I simply just need to do back substitution to come up with what b and c are going to end up being. So here, 3 plus 4a plus b implies that b is equal to 3 minus 4a, which is 3 minus 4 times 1. That's just 4. And the result ends up being a negative 1. So a is 1, b is negative 1. And now we use that information in equation 1 to figure out what c will end up being. So 4 times 1 is 4. 2 times a negative 2. Sorry, 2 times a negative 1 is negative 2. And of course, 4 minus 2 is 2. And you can easily see from that that c ends up equaling 3. So we know here that our final answer is that our function p of x is going to be a, which is 1, x squared, plus b, which is negative 1x, plus c, which is 3, which just ends up being x squared minus x plus 3. So this particular quadratic function polynomial will have all three of these properties. Have a 0.25 on this graph. The rate of change of that function at the 0.25 is 3, and the rate of change of the rate of change will be 2 at that same point. And again, this is our final answer here. Okay, so for our next example, we're going to revisit some concepts that we talked about earlier in this video, in that we're going to find an equation for the line that's perpendicular to the tangent line to this particular curve at the point 3,6. So again, we know that we need to find an equation of a line, but that line is going to be perpendicular to a tangent line, okay? So remember that a line that is perpendicular to a tangent line is called a normal line. And the slope of the normal line is going to be the negative reciprocal of the slope of the tangent line. Okay. So we are trying to find a line that has this slope and it goes through this particular point. Okay. And of course, the function that we're given here is this cubic function. Now, in order to find the slope of the tangent line of this particular function going through this point, we have to take the derivative of this particular function, evaluated at this x value. Okay? And so once we find out this information, then of course we'll know what the slope of the normal line is going to be, which is the slope that is going to be perpendicular to the tangent line. And then we just use the point slope formula to figure out, hey, slope, point, throw it in, figure out the equation of y. All right, so here we know that the derivative of this particular function here is going to be 3x squared minus 9. Using the power rule here, and of course the derivative of any linear expression is just going to be whatever the slope of that linear expression function is. Derivative of a constant is 0. So looking here, we have this derivative. So what this implies here is that the derivative of this function at 3 is going to be 3 times 3 squared minus 9. And here that's 3 squared, which is 9. 9 times 3 is 27. So all this is 27. 27 minus 9 is 18. And that is going to be the slope of the tangent line. So therefore, the slope of the normal line, which is what we actually need, is going to be the negative reciprocal of the slope of the tangent line. So that is just going to be a negative 1/18. Okay? And so if we use that with this point, we can find equation of normal line. Okay, so therefore y minus y1 equals slope of normal line x minus x1, where 3 will be our x1, 6 will be our y1. Here we'll have y minus y1, which is 6, equals negative 1/18 x minus x1, which is 3. And then there we just solve for y. So if I distribute both terms here, it's going to be negative 1/18 x plus 3/18. And of course, 3/18, if we simplify that, that fraction is 1/6. So go ahead and take care of that. Oops, 1/6, not 1/16. All right, and so now finally we just need to add 6 to both sides. So if I add 6 to both sides here, add 6 to both sides there, then we get y is equal to 1/18x plus 6 and 1/6. And of course, 6 and 1/6 as a improper fraction will just be 37/6, because 6 times 6 is 36 plus 1 is 37. So here this will just be 37/6. And so this would be the actual equation of the normal line that we are looking for. So for our next example, is actually tied to our first one. We want to know what is going to be the smallest slope on the curve of this particular function here. That is to say, what is going to be the smallest value of the derivative of this particular function? And at what point on the graph does the curve have this particular slope? Okay, and that should be a question mark right there. Now, if we think about what is going to be the smallest slope here, an easy way to find that out is to say, well, what is going to be the minimum value for the derivative? Okay. Now, one conceptual and very easy way to look at that is to say, well, what's the derivative of this? Okay. If I can find out what the derivative of this is, and then use pre-cal knowledge to tell you what's going to be the smallest value on the graph of that function, life is easy. Here, we already know the derivative is going to be 3x minus 9. If we were to draw this particular function here, it would look something like this. Okay. So this would be the derivative of our function x cubed minus 9x plus 6. Well, we see on the graph of this particular function here that the smallest or the lowest point on the graph here is right here. And of course, that occurs at x equals 0. Okay. Now, remember, this is not a graph of this function. Okay. It is not a graph of this function. What you're seeing here is a graph of the derivative of this function. Okay. So since it's a graph of the derivative, the only thing that we can say here is that the derivative of this particular function has its smallest value at the x value for this point, which is at x equals 0. Okay. So now that we have that, we can say x equals 0 is where dy over dx is smallest. Okay. Now, our question says, at what point on the graph, and that's the graph of the original function, does the curve have this slope? Okay. Well, we know it's at x equals 0. So if we just plug in 0 into this function, we figure out where that is. So therefore, y of 0 is just going to be 0 cubed minus 9 times 0 plus 6, which is just 6. Which means here, the point 0, 6, this is where y of x has smallest slope. And I'm going to put in parentheses here of tangent line. Okay. So again, all we did was say, hey, we know that the derivative of this function, we can calculate that. We look at the graph to see what is going to be the lowest point on there, and that will let us know what the smallest derivative will be. And then afterwards, we use that x value to figure out at what point does that happen. Okay. Now, notice that the derivative of this function, when it is the smallest, is going to be at -9. Okay. So the derivative of this when x is equal to 0 is going to be -9. So what that's communicating to you is that on the graph of this function, if I was to draw it, and that function will look something like this, what it's actually trying to say is that the most that it will decrease instantaneously, which is probably at about right here. If I was to look at the slope of the line going through this point here, the slope of it would be at -9. And that would be the smallest slope, or the most negative slope I would get. Okay. Now, for future reference, this concept of trying to find out where the smallest derivative would be for a particular function, this is code for what we call an inflection point on a graph. Okay. So if you notice here, at the point that I've drawn, and of course this is the point 0, 6, notice that my graph from this point here, from this point on down, it starts to decrease. But when it gets to this point, it's not going to decrease anymore. Okay. So if I was to draw slopes of tangent lines for all these other points, you'll see that these other points I've drawn, the slope of the tangent line will be higher than -9. Okay. So just putting that in your mind, because you are going to see this concept of an inflection point later, and how this particular question was worded was a way to actually describe that without actually saying inflection point. So you may want to write that down in your notes and just kind of keep that as one of the things to think about as you move forward if you're taking a first-year calculus course. All right, so for our last example for this particular set here, we still have some more examples, but this is the last one that's tied to to this particular function here. We want to find the equations, meaning S, meaning more than one, equations for the tangent lines to the curve of this particular function at the points where the slope of this curve is equal to 39. Okay. So again, before we actually do this problem, I'm going to describe conceptually what it's actually asking for. And then after that, we'll algebraically do it. Okay. So conceptually, what we're looking at is a cubic function. And as you see, I've already drawn a graph of what this cubic function might look like here. And this is our y-axis. And here, what we are trying to figure out is what points are going to be on the graph of this function here, where the slope of the function is going to be 39, meaning the instantaneous rate of change is going to be 39. So they said equations, so that means it's going to be more than one. So just kind of guessing here, since the slope of the tangent line is positive, it's going to have to be on an area of the graph where it's going to be increasing. Okay. Also, since we're looking for more than one equation here, where the slope is going to be 39, whatever line I find going through this point, as well as the other point I select, it's going to have to be parallel. Okay. So here I'm going to select a point here, and I'm not being, doing this to scale, but what I'm imagining here is that this point and this point, if I was to draw a line through this point here, I'm going to, things not allowing me to do it here. So let me see if I can. Yeah, so basically, if I'm drawing a line through here and a line through here, those two lines are going to be parallel to each other, meaning that they're going to have the same slope. Now, what we are trying to figure out is this x value here and this x value here, where this happens. Meaning, what are the x values for where, if I go up to the corresponding points and I said, hey, what is the instantaneous rate of change of this function at these x values? They will both be the same, and they will both be 39. Okay. So conceptually, that is what we are doing. Now, to figure that out, again, we know that for this particular function here, if I am going to track instantaneous rate of change, I'm going to have to find the derivative of this particular function. So if I find the derivative of it, and of course we know in this case it's just going to be 3x minus 9. The derivative of this function is going to have to be equal to 39. Okay. And so from here, we have that 3x squared minus 9 is equal to 39. So what this tells us here is that we need to solve this equation for x so that we can figure out these x value locations here. Okay. Now, once we do that, then we can use those x value locations to help us eventually find out what the equations of those tangent lines are. Okay. So again, here, if we find out what x is, that will give us the x coordinates. If we have the x coordinates, we can plug them into this function here, find the corresponding y coordinates, and then after we find both the x and y coordinates for both of these points here, we can use point and same slope to be able to find their corresponding tangent lines. And so that is what we're going to do. So since I already have this started here, I'm going to go ahead and finish up this part here. So if we add 9 to both sides, it's going to be 3x squared is equal to 48. We divide both sides by 3. And this is going to be 16. So x is going to be plus or minus square root of 16, which is plus or minus 4. So we know here that x1 is going to be at minus 4 and x2 is going to be at 4. So that much we already know from information that we've collected so far. Okay. All right, so now that we have this, what we can do now is take this information over and we're going to figure out what's the corresponding y coordinates so that we can find these points and then find the equation of a line. All right, so we see here at x equals plus or minus 4, slope of tangent line is equal to 39. We have that. So now, if we want to figure out what is going to be y of minus 4, we just plug in minus 4 into our function here. And if we want to figure out what y of 4 is, we just plug 4 into our function. So for this first one here, negative 4 cubed is a negative 64 plus 36 plus 6, same as 64 plus 42, which will give us a minus 22 for the first one. And for the second one here, for some reason it's hard to write 4s. So 64 minus 36 plus 6, which is 64 minus 30, which is 34. So what we know here is that slope is going to be equal to 39 at the points. So at points, negative 4, negative 22, and 4, 34. Again, those 4s for some reason are kind of hard to draw on here. All right, so now at this point, we have everything that we need to be able to find both equations of both tangent lines. So to do the first one here, slope is 39, and our point is negative 4, negative 22. And our second one will be slope is 39 at point 4, 34. So for here, y minus y1 equals m tan x minus x1. So this is x1, y1. So we have y minus a negative 22 equals slope, which is 39, x minus x1, which is a minus 4. And that's just y plus 22 equals to 39x, 39 times x plus 4. And then from here, if I distribute I have 39x times 39 times 4. That's 6 with a 3, so that's 156. And we subtract 22 from both sides. That cancels. Y is equal to 39x plus, and that would be 134. And I'll just double check my math just to make sure everything is good. Yep, okay, everything looks good there. All right, so now we will go and do the same thing here. So y minus y1 equals to m10 x minus x1, where this is x1, y1. So y minus 34. Slope is 39. X1 is 4. I'm trying really hard to not have my 4s look like y's, but some reason it's just not letting me do it today. All right. And so now from here, we'll distribute again. This is 39x minus 156. And then we'll add 34 to both sides. All right, and so then this will be a minus 122. And so that will be the other tangent line that we have. And so if you notice, both of these lines have the same slope. The only thing that's different about them is their corresponding y-intercepts. And we expect the y-intercepts to be different, but the slopes to be the same for lines that are parallel to one another. And so if we go back and look at conceptually what we were talking about, if I was to take this line and keep going down, this would be the one where I would have the negative 122 here. And if this one was to keep going up, of course, this, if I keep drawing this up, this would intersect the y-axis at the positive 134, if I remember those numbers correctly. Yeah, so positive 134 on the y-axis here, negative 122 for the other. All right, so for our last two examples here, we're given information about two functions, and what we want to do is find out what's going to be the derivative of that function at a particular x value. And so here we are given how the function is defined. So we see that h of x is equal to g of x divided by 1 plus f of x. And we're given that f of 2 is equal to negative 3, g of 2 is equal to 4, f prime of 2, or the derivative of f evaluated at 2 is negative 2. The derivative of g evaluated at 2 is 7, and we're asked to find out what this is. So the first thing that we need to do is actually just find out what h prime of x is. And since we have the quotient of two functions, we'll need to use the quotient rule to be able to do that. So to find a derivative of this function, we will take the derivative of the low function, not derivative of the low function, but we'll take the low function, which is 1 plus f of x, times derivative of the high function, and the derivative of the high function would just be g prime of x. And so here minus, so low times the derivative of high minus high, which is g of x, times the derivative of the low function here. That didn't write the way I wanted it to. So we have derivative of the low function, and all of that divided by low function squared. Okay. And so now that we have this, the only thing that we need to do now is evaluate the same thing at 2. So everywhere where we have x, we're just going to replace it with a 2. So we're going to go ahead and do that now. Oops, well, that's not how we would do that. So let's go back and undo and try again. All right, so here we're going to erase. Everywhere where we have an x, we're going to put a 2. All right, so this will be a 2 here, 2 here, 2 here, 2 here, 2 there, and we'll get this one down here as well. Two here. All right. So now that we have all the 2's filled in, we can essentially just go in and plug in everything that we need to now. So let's go ahead and do that. So if we look here, we have 1 plus, and then f of 2 is -3, according to what we're told here. G prime of 2 is 7, because that's what we're told here. G of 2 is 4. And here, notice that we're taking the derivative of 1 plus f of 2. So here we know that the derivative of 1, or derivative of any constant, is 0. The derivative of f of 2 is just going to be f prime of 2. So all of this is just going to be f prime of 2. And f prime of 2 is just -2. F of 2 is a -3. Okay. So now that we have all that accounted for here, we'll go ahead and fill in and finish up this particular problem here. So we have 1 plus a -3 is a -2. And -2 times 7 minus 4 times a -2. And all that over here, 1 plus a -3, which is a -2. And we square that. Okay. So this ends up being a -14 plus 8 all over 4. And this is just going to be -6 over 4, which is a -3 over 2. And so this is what our h of 2 actually ends up being here. All right, so for our last example, something kind of similar. So we're given that f of x is the product of some function g of x that we don't know explicitly, and e to the x. But we do know that we have the point 0, 2 on its graph. And we also know that the instantaneous rate of change of that function is going to be 5 at this particular point 0, 2. So what we need to do here to find out what is going to be the derivative of the product of these two functions here at 0 is find out what the derivative of this is and then evaluate it at 0. So f prime of x, we just follow the product rule, which is derivative of the first times the second plus first times derivative of the second. And of course, derivative of the second would just be g prime of x here. And so this lets us know that f prime of 0, of course, the derivative of e to the x is just e to the x. Okay. and the derivative of g of x, we don't need to know that, but we already have this information here. So I'm going to write it, and then we'll take care of doing a correct evaluation here. So now that we have that, since I want to evaluate this at 0, what I need to do is replace all my x's with zeros. So we'll go ahead and do that now. So we got a 0 here, 0 here, 0 there, 0 there. And now we see that e to the 0 is just 1. G of 0 is going to be 2. And g prime of 0 is going to be 5. So we see here that once all this is done, we essentially just have 1 times 2, which is 2, plus 1 times 5, which is 5, and our result here just ends up being 7. So f prime of 0 is just going to be 7. All right, so this concludes the examples for the video on finding the derivatives of functions using differentiation rules. And so remember, this video was about doing application problems involving that. And so, matter of fact, there's one more example that I want to go ahead and do here. But I'm going to do it in a separate video because of the fact that it involves trig functions, and it's a little bit long, and I know this video's already gotten long already. So I'm going to go ahead and end this one, and I'll do the last example on a separate video. I hope to see you there. Take care.